Hey everyone, welcome back, and today let's solve Leetcode problem 2033 titled Minimum Operations to make a Uni-Value Grid. So we're given a 2D integer grid. It's going to have a size of m by n, rows and columns are dimensions if you will, and an integer x as another input. And in one operation we can either add x or we can subtract x from any element or cell in the grid. Now, a uni-value grid is a grid where all of the elements in that grid are equal. And we want to return the minimum number of operations to make that grid uni-value. And if it isn't possible at all, well, we want to return -1. And the way we can make it possible, again, is to add that fixed value or constant or subtract that fixed value or constant x from any cell that we want in our input grid until we get all of the values or all of the cells to be equal in value. So in example 1, we have our input example, or our original input grid, to be 2, 4, 6, 8. And in this case, x is 2. Now what x is 2 really means in the context of this example and in this problem overall is that we can either subtract x or subtract 2 or add 2 to any cell any number of times that we want until we actually get equal values for all 4 cells in this grid. And in this case, it is actually valid. It is actually possible to achieve that constraint, and so we don't have an output of -1, but rather we have an output of 4. And what this 4 as our output signifies, it basically tells us that 4 is the minimum number of operations to make as a whole to get all equal values in this grid. And how would that work? Well, the closest element, or kind of like the middle element, I'm hinting at things to come, that we can get all of the elements to be equal to would be 4. Notice how to get to 4, we only need to have one operation on the 2, we only need to have one operation on the 6, and we really only need 2 operations on the 8. That would be a total operation of 2 plus 1 plus 1, or 4, right? The 2 operations on 8 would be subtracting 2 twice to get to 4. 8 minus 4 is 4. The 1 operation on 6 is to subtract 2 once. 6 minus 2 is 4. And the 1 operation on 2 would be to add 2 once. 1 operation is 2 plus 2 is 4. That's going to be a total of 2 plus 1 plus 1, or 4 minimum operations, right? Now, another very important thing to note is that notice how all of these integers here, the difference between them is all actually divisible by 2, meaning in some number of operations, we can actually make them equal by only adding or subtracting 2, meaning there is actually a divisible by 2 amount, a remainder of 0 for the difference of all of these elements, which is very key, because if this was per se a 7, we'd never be able to hit it, right? 2 plus 2 is 4, 4 plus 2 is 6, but 6 plus 2 is 8. We can never actually equal 7 because 7 minus 2, 5. 5 is not divisible by 2, right? 5 is not divisible by the actual x value amount that we can add or subtract by. So that's also very important and a very important constraint to keep track of. In example 2, we have our input grid to be 1, 5, 2, 3, and in this case, x is 1. Now, when x is 1, it's always going to be possible because we can always just go one step at a time. Everything is divisible by 1. It's just going to take a lot more operations because we're adding and subtracting a lot smaller of an amount. In this case, the minimum would be an operation of 5, minimum number of operations would be the number of operations to be 5 as the minimum. And notice how, again, kind of like that middle value here of all of these elements, that's actually going to be 3 here. To get to 3 from 3, we don't need anything. 5 would be 2 operations, 1 would be 2 operations, and 2 would be 1 operation for a total of 2 plus 2 plus 1, or 5 operations to get all the other elements that are not equal to 3 originally to get to 3, either by subtracting 1 or subtracting x, or adding 1 or adding x to them. In example 3, we have our input grid to be 1, 2, 3, 4, and in this case, x is 2. Notice how the difference between all of these elements, between each pair of elements, is not divisible by 2, at least not all of them are, and so we actually have an output of -1. It is impossible to make every element equal, right? We can get from 2 to 4, we can get from 1 to 3, but we cannot get from 1 to 4, 2 to 3, or 2 to 1. Right, or even 3 to 4 in that matter, because x is 2. If we add 2 to 3, we'd get 5. If we subtract 4 from 2, rather, if we subtract 2 from 4, we'd get 2, and so it doesn't work. So for the constraints here, we said that m and n are the number of rows and columns in the grid, and they're both going to be between 1 and 10 to the 5th power, where m times n is also going to be between 1 to the 10 to the 5th power, and any grid value and x are all going to be between 1 and 10 to the 4th, which brings us to the main observations to really kind of solve this problem. And I was really hinting at this as we saw in the examples before. To kind of formulate it or kind of make it neat in a full sentence here, the main observation to really make in this problem is how do we actually know that a board is possible to solve? How do we actually know we can actually make it uni-value? Well, again, going back to that difference in kind of remainder and divisibility of the x value, we can only modify values by adding or subtracting x to cells. That's the entire operation. So what does that tell us for the actual observation? Well, we need to check whether all of the numbers in the grid share the same remainder when divided by x, right? If they don't, well, then it's impossible to make all the elements equal. And we saw that in examples 1 and 2, that was actually possible. However, in example 3, it was not. Right? Now, assuming that is possible, so once we actually cover that check and we actually assume that it is possible in our input grid, we also then need to then check, okay, we have to actually find the final value that minimizes the total number of operations. Now, going back to that other hint that I was talking about in example 1, 2, and 3, rather just really 1 and 2, why did we choose to go all values to be equal to 4, and why did we choose all values to be equal to 3 in this example? Well, notice how 4 is kind of like in the middle, or one of the middle values in this example, right? 4 is a lot simpler, because let's kind of think about it kind of visually. If we have 2, 6, and 12 as 3 cells in a grid, well, to go from 2 to 12, and assuming x is 2 in this example, to go from 2 to 12, we'd need 5 operations. To go from 6 to 12, we'd need 3 operations for a total of 5 plus 3, or 8 operations. But what if we wanted every value to be equal to 6, the kind of like the middle value in this data set? Well, then to go from 2 to 6, we'd only actually need 3 we'd only actually need 2 operations, and to go from 12 to 6, we'd only need 3 operations. Notice how that's a much more efficient of only 5 operations. What is that telling us? Well, the middle value is always easiest because the other 2 extremities, or the other 2 ends of values, can get to it in less operations, or in less subtracting and adding. Whereas if we wanted to pick an extreme like 2 or 12, we'd need more operations because we have a higher difference between values, and that's obviously not minimizing the number of operations, and it isn't the most efficient of solutions. Right? So, kind of formalizing that again. The median of the grid's values is always going to be the best target value, because that's going to minimize the sum of all the absolute differences between all of the pairs of cells, and that's going to be the most optimal choice to actually transform all the cells to be uni-value. So how are we going to solve this problem? Kind of taking those observations into mind. Well, we're first going to flatten the grid, because of course we need to actually compare all the values. And so a very easy way to do that is actually to convert the 2D grid into a 1D array, to iterate over that and check for that, instead of actually iterating through all the possible cells in a 2D grid. Because flattening it out and actually making it into a 1D array and checking for all pairs like that is a lot easier to iterate over and actually deploy in code than it is with a 2D grid. And we also need to check for that modulo condition, right? Again, to actually check if we have a valid grid. We have to always ensure that all the numbers have the same remainder when we actually divide them by x, so they're divisible by x. That's very important. And then once we actually check for that, and as long as our grid is actually valid, or it is possible to get our grid to be uni-value, then we find our median or target value. That would be the optimal value to transform all the other cells into, because it would be the median of the sorted array. It would minimize the number of operations needed to get all the other values to that value. And then, of course, once we actually grab that median, we then want to actually calculate our operations. Basically meaning we want to compute the number of operations we need to make each element equal to that median. Because at the end of the day, that's going to tell us our answer. So let's go ahead and get into the code of this solution. So like I was just talking about, we want the flat list, or the flattened list. So I'm literally just going to call it flat list. Feel free to call it whatever you'd like in your own solution. And I'm going to do something called list comprehension here in Python. And it's a little bit weird, a little bit goofy, but it should be somewhat easy to understand. It's going to be every value number for every row in the grid for every number in the row. So I believe this is kind of like 2 nested loops here, just in one line. And so this is still going to have kind of like the same complexity. It's just all kind of squished or mushed into one line as we flatten out the list, right? It's going to be every number for every number in each row of the grid. So first we iterate over all the rows in the grid, and in each row we iterate over all the numbers in that row and add it to the flat list of the 1D dimensional list, right? Basically, we're flattening the 2D grid into a 1D list. And this is, I believe, nested conditionals or nested loops here. I believe it's called nested list comprehension. I believe if that's a thing, we iterate through each row, through each number in the row, and then we collect all those values and combine it into a single list in the flat list array that we just initialized on line 3. Once we get that flat list, now let's actually sort them because we want to actually easily find the median value. So I'm literally just going to call the sorting method or sorting function that's built into Python. So flat list.sort on the flat list, right? Basically, we're sorting it because we want to find the median value, and a very easy way to do that is in sorted list because it would literally just be the middle value, and so we're going to just sort it to actually get it very easily and very quickly in an efficient manner. Because again, the median value is what's going to minimize the number of moves that we need, right, to actually minimize the number of operations. Now, once we get that, now let's actually check, is our transformation even possible? Is it even possible to get all the numbers to be equal? That's kind of like our modulo operation or our remainder check. So let's first initialize our remainder. And I'm going to initialize it to be flat list at index 0, the smallest value in the sorted kind of sorted list flat list, and it's going to be modded by x, right? Kind of taking that remainder, right? Now, we're taking the remainder of the very first number when it's actually divided by x. Why? Because if the transformation is actually possible, meaning we do actually have a valid grid, we know all of the elements have to share this remainder. So theoretically, we could have taken any value. I just took the initial value because I thought it was going to be easiest to kind of comprehend here. So now let's actually check if every value in the flattened list or every value in the cells in general for the input actually does have the same remainder with, well, the x value. So for every number in the flattened list, and again, this is why we flattened it, because we'd have to iterate it over multiple times of the 2D grid if we didn't flatten it out, which obviously wouldn't be too handy in this deployment. Now, for every number in this flattened list, or basically all these cell values in the grid, if any number modded by x, if it's not equal to the remainder that we actually calculated back on line 5, if it's a different value, then we immediately have to return -1 because we know it's going to be impossible to actually get this value grid to be Uni-Value, right? Again, we're really just iterating over all the values in the flat list, and we're checking if each number actually has the same remainder when it's actually divided by x as the initial value. If any number has a different remainder, that means it's impossible to make all the numbers equal using x because we can only subtract or add that fixed constant value x to the input, right? So again, we saw with in example 3, right? If we had like 1, 2, 3, and 4, x was 2, 1 modded by 2 has a different value than 2 modded by 2, which has a different value than 3 modded by 2, which has a different value than 4 modded by 2. Since they're not all equal, we can't get all these values to also be equal, and so we'd have an invalid input, meaning we'd have an -1 output, because that kind of tells us that it's impossible to make all the numbers equal using x. We have to return -1 immediately. We don't have to check anything else. We simply return -1 if that is the case. Now, if it isn't the case, if we haven't returned -1 yet, well, now let's actually find the median and continue with our logic. So first, how do we get the median? Well, the median is, again, basically just the middle value of the flattened list. And a very easy way to check for the middle value of the flattened list is the number of elements divided by 2, because that would give us the exact median or middle value in the sorted list. It would be the length of the flat list integer divided by 2 in Python. So it's going to be flat list, and it's going to be the index of the length of flat list divided by 2, because the length of the flat list would simply be the number of elements that we have, and that divided by 2 would be the middle index. And so we get the flat list at that median or middle index, and we kind of extract that actual median value, right? We're finding that median value by selecting the middle element of the flattened list. Again, that median is going to be the optimal target because it would minimize the total absolute differences and the total number of operations that we need to get all the other elements to be equal to it. Now, we have to actually calculate that minimum operations once we found the median. And again, we're going to be doing this in one line. Basically, it's going to be the sum of the absolute value of every single value num minus that median value divided by x for every single number in the flat list. And hopefully this should seem somewhat intuitive to you. Basically, for every single number in all the cells value that we have in all the flat lists, we're going to get the absolute value of the difference between them, and we're going to divide that by x, because dividing it by x will so the absolute value of the num minus median is the total distance that we have to cover to get from the current number to that median. And if we divide that by x, that would tell us the number of operations that we need to go from there. And of course, we have to take the sum, because the sum would kind of get all of those distances for all of the elements to be the total number of operations we need for all of the elements to get to that median value, right? Again, we're calculating the total number of operations by summing up the absolute differences between each number and the median, and we divide it by x to get the accurate number of operations for each number, right? And that really works because we're only allowed to add or subtract that fixed constant value x. And so the number of operations needed for each element would simply be that number minus the median, take the absolute value of that, because we don't want negative distances, and we're going to divide that integer by x. And effectively, once that's done, we simply want to return the number of operations that we actually calculated, because that would actually tell us the number of operations that's minimized to actually get all the values equal to that median and to actually get all the values equal in the entire grid. So unless I made any syntax errors here, this should be accepted and this should be a valid solution. Okay, so it looks like my Leetcode just kind of broke, but yeah. That's kind of the solution for this problem. I hope you guys enjoyed that part. Now, so I'm going to go ahead and talk about how the solution works as a whole. Effectively, we first flatten the grid into a 1D list for easy iteration. Then we actually check if the transformation is possible using that modulo condition and logic. If it is, well, then we find the median value as the target value to get all the other cells to be equal to, and then compute the minimum operations needed to transform all of those numbers to the median, right? And it's very optimal because using that median would minimize the sum of absolute differences across all of the cells, and that would always ensure the fewest operations, like we saw in the examples as well. So for the runtime complexity here, it's quite large because of the number of variations and operations that we're doing. So I'm going to comment it out. Runtime complexity. Looks like I added an extra L there for no reason. So it's actually going to be something quite complex, and I'll explain how it works. It's going to be big O of m multiplied by n log of m times n. Right? Now, why do we have such a kind of obscure runtime complexity? Well, the reason why is to actually flatten the grid, that's going to be big O of m times n, because we need all the cells, meaning m times n. To actually sort the list, it would be big O of m times n times the log of m times n, because again, that's kind of n log n, that's kind of like the sorting template or algorithm or runtime for sorting algorithms. Now, to actually check the modulus condition and to actually compute the minimum number of operations, again, it would be big O of m times n for all the cells. And so overall, it would be big O of m times n log m times n, right, for that sorting. And sorting is kind of like our bottleneck. So for the memory or space complexity here, it's actually relatively simple, especially compared to the runtime complexity. I'll add space/memory. People like to call it memory instead of space. Doesn't really matter. Both are correct. It's going to be very simply just big O of m times n. Right? Really just the number of cells we have or the dimensions of the grid, big O of m times n, because we actually sort the input grid into a flattened 1D array. That's going to take a big O of m times n space, because really we just have every single cell exactly once stored in that grid, and or rather in that 1D array, and all the other variables would be just integers that would take big O of 1 or constant times space. And so the overall runtime, or rather the overall memory or space complexity is big O of m times n, basically kind of just linear, if you will. Right? So if you guys enjoyed the solution and learned something new, please consider liking this video and subscribing to my channel. And without further ado, I will see you guys in the next video. Bye-bye.